Tonight, step outside if you can. Find a spot away from the lights, somewhere the sky actually goes dark, and look up. Give your eyes a few minutes to adjust. Let the stars come in, and if you are somewhere far enough from a city, you will see something that billions of people alive right now have never seen in their lives. A pale river of light running across the sky from one horizon to the other. Uneven, slightly smeared at the edges, brighter in some directions than others, with dark patches that look like gaps in the glow. That is the Milky Way, your galaxy, the actual structure you live inside, visible to your naked eye on a clear night. And the thing is, almost everyone who has ever looked up at that band of light has carried in their mind, alongside the actual view, a second image, a different picture entirely, a clean, sweeping spiral galaxy seen from far outside, glowing at the center, arms curling outward through the dark, a picture that feels like what you are really looking at, the true shape of the thing behind the glow. Somewhere on that picture, near one of the outer arms, there is usually a small marker, an arrow, a label. It says, "You are here." You have seen that second image your entire life. In textbooks, on NASA websites, in the opening minutes of documentaries about space, on the walls of every planetarium in the country. For most people, it does something useful and satisfying. It takes the formless glow you see with your eyes and gives it a shape. It says, "We figured this out. Here is what it actually looks like. Here is where you fit inside it." That image is not a photograph, not one version of it, the famous one with the golden bar at the center, the blue-tinted one with the 4 clearly labeled arms, the one your teacher projected in 7th grade. None of them were taken by a camera pointed at our galaxy from the outside. Every outside view of the Milky Way you have ever seen was built by scientists and artists working from radio telescope data, infrared surveys, star catalogues, and decades of careful inference. The most widely shared version was created by a visualization scientist named Robert Hurt at Caltech. He did not capture our galaxy from a distance. He made a decision, based on everything astronomy had measured up to that point, about what the Milky Way probably looks like, and then he painted it. This is not a criticism. The work is extraordinary, and it represents genuine scientific knowledge made visible. But there is a difference between a photograph and a reconstruction. And that difference matters here more than it has ever mattered before. The image showing you where you live is a hypothesis made visible. No spacecraft has ever traveled far enough to photograph the Milky Way from outside. No telescope has captured our galaxy the way we capture Andromeda, as a whole object at a distance where its full shape is visible. We are inside the Milky Way, buried in its disk, surrounded on every side by gas and dust and hundreds of billions of stars, and the light from most of those stars reaches us filtered, scattered, and rerouted by material that stretches for hundreds of light years in every direction. We have never seen our home from the outside. We have only ever measured it from within and reasoned our way toward a picture of the whole. And here is the part that changes everything. The region of the galaxy we understand least well, the part of the map still actively being revised by researchers right now, is not some distant region on the far side of the Milky Way. It is the arm directly around us, the structure called the Orion Arm, the place the "You Are Here" marker is pointing to. The address on the most famous map in science is the part of the map that is still being redrawn. Go back outside if you stepped in. Look up at that band of light again. You are not just looking at a pretty sky. You are looking along the plane of a structure whose shape is genuinely uncertain, whose length is actively debated, and whose classification, what kind of thing it actually is in the architecture of the galaxy, has not been settled by the best instruments humanity has ever built. 2 questions need to stay in the room for everything that follows. How do you map a home you can never step outside of? And what does it mean to live inside a map that keeps getting corrected? Most people, if you ask them where Earth is in the universe, can answer in about 10 seconds. Earth is in the solar system. The solar system is in the Milky Way. The Milky Way is in the universe. It is a satisfying answer. It has a nested elegance to it. Each container inside a larger container. Each step of the address one level bigger than the one before. You can say it quickly and feel that you have said something true. But there is a layer missing from that answer. A layer that sits between the solar system and the full Milky Way. And it is the most immediately relevant address most people have never thought about. The solar system does not float freely inside the Milky Way the way a single marble sits loose in a jar. It lives inside a specific structure, a specific arm of the galaxy, a concentrated river of stars and gas and dust arranged in a rough spiral shape, wrapped around the galaxy at a particular distance from the center, with a particular history and a particular character. That structure has a name, the Orion Arm. You might also see it called the Local Arm, or the Orion Cygnus Arm, after two of the most prominent features visible within it from our location. The Orion Nebula, that faint smudge below the belt of the constellation Orion on winter nights, is one of the most active star-forming regions in our part of the galaxy. The Cygnus region, rich with young stars and molecular clouds visible in summer, is another prominent feature of the same structure in a different direction. These names reflect real physical landmarks in a real place. But the name you will encounter most often in older textbooks and many scientific papers is neither of those. It is the Orion Spur, or sometimes the local spur. That word, spur, is doing a significant amount of work in a very small package. And understanding what it means is essential to understanding why the question of where we live is more complicated than the standard answer suggests. In geology, a spur is a ridge that branches off from a larger mountain range. Secondary by definition, it exists in relation to something bigger. In railway terminology, a spur line is a short track that branches from a main line. It serves a local purpose but does not go anywhere. The main line does not already serve better. In both cases, the word communicates the same fundamental idea. This is not the main feature. This is a minor appendage attached to the main feature. When astronomers applied that word to the structure the solar system lives in, they were making a specific scientific claim. The Orion Arm is not one of the primary spiral arms of the Milky Way. It is a secondary structure, a local bridge sitting between two larger and more significant arms. The Perseus Arm runs on one side of us. Farther from the galactic center, the Sagittarius Arm runs on the other side, closer to the galactic center, and between them, according to the model that dominated for most of the 20th century, the solar system sits in a minor connecting feature, a side street between two main avenues, a footnote in the galaxy's structural story. For decades, that picture held. The data available was consistent with it. The concentrations of young stars and gas near the sun traced a feature that appeared, in the maps produced by radio surveys and optical studies, to be relatively short and narrow compared to Perseus and Sagittarius. It seemed to connect them rather than rival them. And then the measurements got better. A series of studies using a technique called very long baseline interferometry, which effectively uses the entire diameter of Earth as a radio telescope to achieve extraordinary precision in measuring distances to specific star-forming regions, began producing results that did not fit the old picture comfortably. The local structure appeared longer than earlier maps suggested, better organized. The angle at which it curves around the galaxy fell in ranges more consistent with genuine spiral arms than with a passive interarm bridge. Researchers who had spent careers studying the local structure started using different language in their papers, shifting from spur to arm in ways that were deliberate rather than casual. The debate is not settled. Careful researchers still disagree about what the evidence fully supports, but the direction of the evidence has been consistent. The structure we live in has been underestimated, possibly for decades, and the word spur, which once felt like a comfortable and accurate label, has started to feel like a question that was mistaken for an answer. Here is what that disagreement means at the level of where you actually live. The label on the "You Are Here" marker is contested. What kind of place you live in? Whether you occupy a significant feature of one of the great spiral galaxies in the universe or a minor local bridge between larger features, is an open question being actively worked on by real scientists using real data that does not yet have a definitive resolution. In astronomy, names often reveal what scientists think a thing is. When you call something a spur, you are encoding an assumption about its nature into the vocabulary everyone uses to discuss it. That encoded assumption shapes how new data gets interpreted and which questions get asked. The ongoing shift from spur to arm in the language of some researchers is not a semantic preference. It reflects a genuine change in what the evidence supports, and an argument about where the evidence is pointing that has not yet found its conclusion. The structure you live in is real. The gas and stars and history of the place are real. The question is whether the map describing it has been too simple from the beginning. Are we living in a true arm of the Milky Way, or only in a local spur between greater structures? That question is going to follow us through everything that comes next. On a clear night, far enough from city lights that the sky goes genuinely dark, you can see the Milky Way with nothing but your own eyes. It runs across the sky as a pale, uneven river of light, brighter in some directions, darker in others, with patches of obscuration that look like gaps in the glow. People who see it for the first time often go quiet. Something about it bypasses the part of the brain that processes information and lands directly in the part that processes awe. You are looking at the galaxy, the actual galaxy, in real time, with your own eyes. No instrument required, and that experience, as genuine and as moving as it is, tells you almost nothing about the structure of what you are looking at. When you stand under that sky and look at the band of the Milky Way, you are seeing the combined light of hundreds of billions of stars compressed into a two-dimensional smear by the simple fact that you are inside the disk and looking outward along its plane. You are not seeing arms. You are not seeing the central bar. You are not seeing the shape of the galaxy from any useful angle. You are seeing light the way you would see the glow of a city if you were standing in the middle of it at street level on a foggy night. You know there are buildings all around you. You can see lights in every direction, but the fog and the proximity and the sheer density of the surroundings prevent you from seeing the city's layout, its streets, its neighborhoods, its shape from above. All you have is glow. Now consider something that should feel genuinely strange once you think about it carefully. On that same clear night, if you know where to look, you can see the Andromeda Galaxy. It appears as a faint smudge in the constellation of the same name, visible to the naked eye as a slightly elongated blur of light. It is 2.5 million light-years away. That number is so large it barely registers as a quantity. So try to feel it differently. The light reaching your eyes from Andromeda left that galaxy before the first members of the genus Homo walked on Earth. It has been travelling through empty space for longer than our entire evolutionary lineage has existed. And it is arriving at your eye right now. This moment, tonight, and yet, with a decent pair of binoculars, you can begin to make out Andromeda's structure. You can see that it is elongated. You can see the brighter concentration at its core. With a modest telescope, you begin to resolve its spiral disk, its satellite galaxies, its overall shape as a coherent physical object sitting in space at a definable location. Andromeda is 2.5 million light-years away, and you can study its shape on a Tuesday night from your backyard. The Milky Way is the galaxy you are physically inside, and you cannot see its shape at all. This is not a minor inconvenience of astronomy. It is the central, defining problem of understanding our own galaxy, and it is worth staying with the full weight of it before moving on. Distance, which is normally the enemy of observation, which normally makes things harder to see and harder to understand, has made Andromeda more accessible as a structural object than the Milky Way, because Andromeda is out there, complete, a whole object at a distance that makes it possible to see it as a thing. The Milky Way is in here, surrounding us on every side, and looking at it from inside is like trying to understand the architecture of a building while you are standing inside one of its walls. You cannot see the forest when you are one of the trees. But the problem runs deeper than perspective, and this is the part that took astronomers a long time to fully come to terms with. Even if some hypothetical spacecraft could carry us above the plane of the Milky Way and give us a genuine outside view, the picture we would see would not be clean. Between us and the structure of the galaxy, in every direction we might look, there is material that blocks, scatters, and distorts visible light. Astronomers call it the interstellar medium, and one of its most consequential ingredients is dust. Interstellar dust is nothing like the dust on your bookshelf. It consists of microscopic particles, grains of carbon and silicate minerals and frozen molecules, some of them smaller than a single wavelength of visible light. These grains are not evenly spread through space. They concentrate along the plane of the galactic disk, precisely in the same regions where gas is densest and star formation is most active, which happen to be exactly the regions that carry the most information about spiral structure. When visible light from a distant star tries to travel through a thick dust cloud, the dust absorbs it, scatters it, stretches its wavelength toward the red end of the spectrum. By the time that light reaches a telescope, it has been altered enough that extracting reliable distance and position information from it becomes extraordinarily difficult. The center of the Milky Way sits roughly 26,000 light-years from Earth. In the direction of that center, the dust along the galactic plane is so thick that visible light from the galactic core simply cannot reach us. Point an optical telescope at Sagittarius, the constellation where the galactic center lies, and you see stars in the foreground. Then a progressive darkening as the dust builds up, and then nothing. The actual center of our galaxy, where a supermassive black hole called Sagittarius A star sits surrounded by a dense cluster of ancient stars, is completely hidden from human eyes and from any instrument that works in visible light. We live in a galaxy whose own center we cannot see with optical telescopes. The dust problem does not stop at the galactic center. Throughout the disk, wherever there are concentrations of gas and active star formation, wherever the spiral arms are most clearly defined, there is dust. The very regions that carry the clearest signatures of spiral structure are the regions most thoroughly obscured by the material that defines them. Trying to map the Milky Way's arms in visible light is like trying to read a book through the pages themselves. The information is there. The medium carrying it is also the medium blocking you from reading it. This was the state of galactic astronomy for most of its history. Astronomers knew they lived in a spiral galaxy because other galaxies of similar type were visible and well studied. They could see by analogy roughly what the Milky Way should look like. They could measure properties of nearby stars in visible light and build a detailed picture of the local stellar neighborhood. But the actual large-scale structure of the galaxy, the positions and extents of the arms, the nature and orientation of the central bar, the overall architecture of the home we live inside, was hidden, not hidden by distance, hidden by proximity, by dust, by the fundamental problem of trying to see a thing when you are embedded inside it, and the thing itself is made partly of material that blocks your view. Here is the sentence that captures the situation most directly. We can photograph a galaxy 2.5 million light-years away. We cannot photograph our own from the outside. That asymmetry is not going away. No mission being planned. No telescope being designed. No technology under development within any timescale connected to human civilization will give us a genuine outside view of the Milky Way. We are committed to the inside perspective permanently. The only way forward has always been to improve the measurements made from within, to find ways of probing the galaxy's structure that do not depend on the visible light that dust so thoroughly defeats. And improving those measurements required learning to look at the sky in ways that have nothing to do with what human eyes evolved to detect. If visible light cannot give us the map, what can? Picture a room with no windows and no doors that open to the outside. You are inside it. You have been inside it your entire life. And so has every other person who has ever tried to understand the shape of the building it belongs to. The walls around you are covered with material that gives off signals of various kinds. Some of those signals can pass through the walls and come back, carrying information about what lies beyond. Others cannot. Your job is to figure out the shape of the building you are inside, using only what you can detect from where you stand, knowing you will never be able to step outside and look back at it from a distance. That is the situation galactic astronomers have always been in, and the history of how they have responded to it is one of the more remarkable stories in the history of science. Not because every answer they found was right, but because of the ingenuity with which they kept finding new ways to ask the question. The first major breakthrough came in the early 1950s, from a completely different part of the electromagnetic spectrum than visible light. A Dutch astronomer named Hendrik van der Hulst had predicted in 1944 that neutral hydrogen gas, the most abundant element in the universe in its most basic form, should emit radio waves at a very specific wavelength, 21 centimeters. The physics involves a tiny energy difference between two quantum states of the hydrogen atom's electron spin, which occasionally causes the atom to release a photon at that exact wavelength. Any individual hydrogen atom does this extremely rarely, perhaps once every 11 million years. But the Milky Way contains an almost unimaginable quantity of hydrogen, and when you add up the emissions from billions upon billions of atoms spread across the galactic disk, the combined signal becomes detectable from Earth. The critical property of 21 centimeter radio emission is that it passes through interstellar dust almost without effect. The same dust grains that completely block visible light are essentially transparent to radio waves at that wavelength. When an astronomer points a radio telescope at a region of the sky thick with dust that would be impenetrable to an optical telescope, the 21 centimeter signal comes through cleanly, carrying information about hydrogen gas distributed across enormous distances. In 1951, 3 groups of astronomers working independently in the United States, the Netherlands, and Australia detected the 21 centimeter line from the Milky Way within weeks of each other. Within a few years, systematic radio surveys using this signal had begun to reveal concentrations of hydrogen spread across the galaxy in patterns suggesting spiral structure. The maps were rough and contested. Converting a radio signal into a position on a map required knowing how the galaxy rotates, and the rotation model carried significant uncertainties. But the outlines of something real were becoming visible. Long concentrations of gas tracing, elongated features that behaved like the kind of structure you would expect from spiral arms. Each new tool did not simply sharpen the map, it changed what the map was allowed to be. The second transformation came from learning to see in infrared light. Infrared radiation sits just beyond the red end of the visible spectrum, at wavelengths longer than what human eyes can detect. Longer wavelengths penetrate dust more effectively than shorter ones, which means an infrared telescope looking through a dust cloud sees considerably more than an optical telescope aimed at the same region. The advantage is not absolute. Dense enough dust can block even infrared light. But for most of the galactic disk, infrared observations reveal structures that visible wavelengths cannot reach. The most consequential result of infrared astronomy for Milky Way science was the confirmation of the central bar. For decades, the structure of the Milky Way's center remained poorly understood because galactic plane dust made optical observations of the core nearly useless. Astronomers suspected, based on comparisons with similar galaxies, that the Milky Way might have an elongated bar of stars at its center rather than a smooth round core, but confirming this from inside the disk, through the obscuring dust, was extremely difficult in visible light. Infrared surveys in the 1980s and the landmark 2-micron all-sky survey, completed in 2003, cut through the dust well enough to reveal the bar directly. The Milky Way is a barred spiral galaxy. That classification, which reads like settled textbook fact now, was genuinely uncertain for most of the 20th century and was only established by instruments that did not observe invisible light. The third transformation was the one that made everything before it looked like rough sketching. In December of 2013, the European Space Agency launched a satellite called Gaia. Its mission, reduced to its simplest form, was to measure where stars are. Not a few stars, not a few thousand, more than 1 billion stars, with a precision that had no precedent in the history of astronomy. The technique Gaia relied on is called parallax. As Earth moves around the Sun over the course of a year, nearby stars appear to shift slightly against the background of more distant stars. The size of that shift depends directly on the star's distance. Closer stars shift more. More distant stars shift less. Measure the shift precisely enough, and you have the distance through pure geometry, without any assumptions about the star's physical properties. Before Gaia, parallax distances of high precision had been measured for a few 100,000 stars, mostly within a few thousand light-years of the Sun. Gaia was designed to extend that capability to more than 1 billion. The first major data release came in 2016. The second, in 2018, provided parallaxes and motions across the sky for more than 1,300,000,000 stars. The third release, in 2022, added further refinements along with new data on stellar chemistry, binary star systems, and variable stars. Astronomers who had spent entire careers working with catalogues of thousands of precisely measured stars suddenly had access to catalogues of more than 1 billion. What Gaia made possible, above all, there was a three-dimensional map of the local galaxy, built not from estimated distances with large uncertainties, but from direct geometric measurements precise enough to place individual star clusters at their actual locations in space. For researchers studying the structure of the Orion Arm, this changed everything about what questions could be asked and what answers were within reach. Young open clusters, groups of stars that formed together from the same molecular cloud within the last few 100 million years, are the most reliable traces of spiral structure because they mark the locations where gas has recently been compressed enough to trigger star formation, which are precisely the locations where spiral arms express themselves most clearly. Before Gaia, the distances to most open clusters were estimated from photometry, comparing apparent brightness to expected brightness and working backward. These estimates carried uncertainties large enough to blur the three-dimensional arrangement of clusters into ambiguity. Gaia replaced those estimated distances with geometric measurements for thousands of clusters, and the picture of the local spiral structure snapped into a new kind of focus. What that focus revealed about the Orion Arm is what the next several chapters are about. But before going there, the broader point about the mapping project deserves to be held for a moment. Radio astronomy let us hear the galaxy through the dust. Infrared astronomy let us see through the dust to structures optical telescopes could not reach. Gaia let us measure the three-dimensional positions and motions of 1 billion stars with a precision that redraws the local map. Each of these tools did not simply add more data to an existing picture. Each one revealed that the picture built from previous tools had been missing something real. The galaxy that emerged from infrared surveys was not the galaxy that radio surveys alone had suggested. The galaxy that emerged from Gaia data was not the galaxy that infrared surveys had fully captured. This pattern has a lesson in it that matters for everything that follows. The map we have right now is not the final map. It is the best map current tools can produce. When the next generation of tools arrives, the map will change again, not because previous researchers were careless, but because each instrument reveals only what its particular capabilities allow it to see. The room has no windows, but every new instrument is a different way of listening to the walls. And when the tools became better, one local feature on the map began to demand a second look. Science rarely changes its mind all at once. The more common pattern is slower and less dramatic than that. Evidence accumulates at the edges of an existing picture. Individual measurements that do not quite fit get noted, set aside, then noticed again by different researchers working independently. A threshold gets crossed, not with a single decisive experiment, but gradually, the way a river changes course through soft ground. The old channel does not disappear immediately. For a while, both channels exist at the same time. People standing on the bank argue about which one is the real river. Eventually, the water decides. The debate over what to call the Orion Arm has been following that pattern for roughly 2 decades, and the water has not fully decided yet. Understanding how the argument started requires going back to the conditions under which the original picture was built, because the original picture was not careless. It was the honest product of the tools available at the time. And understanding why those tools produced an underestimate of the local structure is what makes the current debate meaningful rather than simply a correction of an old mistake. In the decades following the detection of the 21-centimeter hydrogen signal in the early 1950s, radio astronomers worked intensively to use that signal to map the Milky Way's spiral structure. The approach was logical. Hydrogen gas concentrates in spiral arms. Detect and map the hydrogen, and you trace the arms. The technique was genuinely transformative. For the first time, astronomers could probe the galaxy's large-scale structure across distances that visible light surveys could never reach. But the maps that came from early radio surveys carried a source of uncertainty that did not always receive the emphasis it deserved. Converting a hydrogen radio signal into a position on a map requires knowing the cloud's distance. Distance cannot be read directly from the radio emission. It has to be inferred from the cloud's velocity, specifically from the Doppler shift of its 21-centimeter signal as the cloud moves toward or away from Earth. To convert that velocity into a distance, you need a model of how the galaxy rotates, how fast gas at different distances from the galactic center moves in its orbit. That rotation model has to be assumed before the map can be built. In the 1950s and 60s, the rotation model was imperfectly known. Errors in the assumed rotation curve produced errors in the inferred distances, which produced errors in the positions of features on the map. Some of those errors were substantial. Features that appeared as distinct structures on some maps turned out on closer analysis to be the same feature viewed through a distorted lens of incorrect distance assumptions. Other features that should have been clear were blurred by the uncertainties into shapes that could be interpreted multiple ways. In this environment of genuine measurement difficulty, the local structure near the Sun was easy to underestimate. The hydrogen concentrations near the solar system traced a feature that appeared, in the maps of that era, to be shorter and narrower than Perseus or Sagittarius. The young stars and star-forming regions visible in the local neighborhood in optical surveys did not seem to extend in a way that obviously rivaled those larger structures. The most natural interpretation of the available data was that the local structure was secondary, a bridge, a connector, something positioned between the main features rather than belonging among them. And the word Spur, once attached, began to do what names in science always do. It shaped expectations. New data got filtered through the existing classification. If you already believe you are in a spur, a measurement showing the local feature extending somewhat farther than expected does not automatically overturn the label. It gets noted, discussed, and usually absorbed into the existing picture with some adjustment around the edges. The framework persists until the weight of contradictory evidence becomes too heavy to accommodate. That weight started building seriously in the 2000s. A series of studies using very long baseline interferometry began measuring distances to specific star-forming regions in the Milky Way with a precision that radio velocity methods could not approach. The technique combines signals from multiple radio telescopes spread across thousands of miles to achieve angular resolutions far beyond what any single telescope can reach, applied to the radio emissions from masers, which are natural radio amplifiers produced by molecules like water and methanol in star-forming regions. Very long, baseline interferometry can determine parallax distances to those regions with the same geometric directness that Gaia later applied to optical stars. These parallax distances did not require assumptions about galactic rotation. They were clean geometric measurements. And when researchers plotted the star-forming regions of the local arm using these distances, the feature that emerged looked different from the Spur model's expectations. A landmark study published in 2014, part of a project called the Bar and Spiral Structure Legacy Survey, placed a series of local arm star-forming regions using precise parallax measurements and found a feature that was longer, better organized, and geometrically more consistent with the major spiral arms than earlier maps had suggested. The pitch angle of the feature, the angle at which it curves away from a perfect circle around the galactic center, fell in ranges comparable to those measured for Perseus and Sagittarius. The distribution of star-forming regions along its length looked less like a passive interarm bridge and more like an active spiral feature, sustaining ongoing star formation across a coherent structure. The authors used careful language, as good scientists always do when pushing against established pictures, but the implication of their measurements was clear. The local structure had been systematically underestimated, likely because the tools used to characterize it in earlier decades were not precise enough to show what it actually was. Gaia reinforced this picture further. Open cluster analyses made possible by Gaia's three-dimensional precision traced the local arm to distances, and with a coherence that added weight to the case for treating it as a genuine spiral feature. Multiple research groups, working independently and publishing in the years following Gaia's second and third data releases, found a local structure longer and more organized than the classic Spur model, accommodated comfortably. Some of these researchers shifted their language accordingly. Papers that had casually referred to the Orion Spur began using Orion Arm or local arm instead, not as a casual preference, but as a considered reflection of what the improving evidence supported. But here is where honesty requires slowing down and not letting the narrative carry the argument further than the evidence warrants. The debate is not over. The classification of a true major spiral arm involves more than geometry. In the technical language of galactic dynamics, a genuine major arm is associated with a density wave, a self-sustaining pattern of gravitational compression that propagates through the galactic disk, triggers star formation as gas clouds pass through it, and persists over multiple galactic rotations. Demonstrating that the Orion Arm meets that criterion requires more than showing it is long. It requires understanding its dynamics, how material moves through it, how long the feature has persisted, and how it relates to the galaxy's overall large-scale gravitational structure. Those questions are harder to answer than questions about position. They require precise velocity measurements in addition to precise position measurements. They require dynamical models that can be tested against data collected from inside the structure. And they require a level of understanding of the Milky Way's large-scale gravitational organization that the field has not yet fully achieved. Different research groups, using different datasets and different modeling assumptions, have reached different conclusions about the Orion Arm's dynamical significance. The argument is real, conducted by careful people who take both the data and its limitations seriously. The honest position today sits between the old Spur picture and the full major arm picture. The evidence accumulated over the last 2 decades makes a strong case that the Orion Arm is a more substantial structure than the word Spur implies. But declaring it definitively equivalent to Perseus or Sagittarius as a primary density wave feature goes beyond what current evidence fully supports. What the argument has revealed, regardless of how it ultimately resolves, is something worth holding on to. The name on the map was encoding an assumption. The assumption was built from the best available data at the time. When the data improved, the assumption began to look too simple. The process of science, the accumulation of better measurements applied to the same question over decades, has moved the picture in a clear direction without yet delivering a final verdict. The local arm is not what the Spur label implied. What it actually is, in the fullest technical sense, remains a genuine open question. We do not merely live in a place whose map is unfinished. We live in a place whose name is still an argument. That argument matters beyond the technical question of classification. A minor spur and a genuine spiral arm are different kinds of places. They have different histories of star formation, different densities of molecular gas, different relationships to the galaxy's large-scale dynamics. The specific character of the Orion Arm, whatever that character turns out to be, shaped the conditions in which the solar system has been moving for the last several billion years. Understanding what kind of structure we live inside means understanding something real about the nature of the environment that made this solar system possible. If even the name of our home is unsettled, what does the neighborhood itself actually look like? Pull back from the large-scale debate for a moment and look at what is actually around us. The Orion Arm as a whole is a structure whose full extent is still being measured and whose classification is still contested. But the immediate neighborhood, the specific region of the arm the solar system has been moving through for the last several million years, is something that can be described with considerably more confidence. And what it turns out to be is stranger, more historically specific, and more contingent than most people imagine when they first hear about it. Start with the most immediate physical fact about where the solar system actually sits. We are inside a bubble. The local bubble is a region of interstellar space roughly 1,000 light-years across in many directions, though its shape is irregular rather than spherical. The gas inside this region is dramatically different from the typical interstellar medium of the galactic disk. It is extraordinarily hot, with temperatures in the range of 1,000,000 degrees in some estimates, and extraordinarily thin, where typical regions of the interstellar medium in the Orion Arm have gas densities of roughly 1 hydrogen atom per cubic centimetre. The interior of the local bubble has densities closer to a few hundredths of an atom per cubic centimetre. By the standards of the interstellar medium, we are sitting in a near vacuum. This cavity was not always here. It was carved. Between roughly 13 million and 2 million years ago, a sequence of massive stars formed in this region of the galactic arm, lived their short, violent lives, and died in supernova explosions. The exact number of these supernovae is not known with certainty, but estimates range from roughly 15 to more than 20 individual explosions occurring in sequence over millions of years. Each explosion sent a powerful shock wave expanding outward through the surrounding interstellar medium, heating the gas, compressing it at the expanding front, and pushing material away from the explosion site. Successive explosions reinforced and extended the cavity created by earlier ones, gradually excavating the region to roughly its current dimensions. The solar system arrived in this region of space, carried along its orbit around the galactic center. Roughly a few million years ago, it did not create the bubble. The bubble was already there, carved by stars that no longer exist. The solar system drifted into it the way a traveler might walk into a clearing in a forest, without having had anything to do with how the clearing came to be. Our neighborhood is not a crowded room. It is a cavity carved by dead stars. The boundary of the local bubble is not a sharp wall. It is a region where the hot, thin gas of the bubble interior gradually transitions into the denser, cooler interstellar medium outside. That boundary is marked by shells of compressed gas and dust pushed outward over millions of years by the ancient supernova shockwaves. And those shells, dense with compressed material, are in many places actively forming new stars right now. The violence that created the emptiness we inhabit also pushed the surrounding material into configurations where gravity has been pulling things together for millions of years. Some of the most prominent star-forming regions visible from Earth sit near the boundary of the local bubble. The same sequence of destructive events that cleared out our immediate neighborhood may have contributed to triggering the star formation happening at its edges today. The deaths of old stars seeded the conditions for the birth of new ones. This is not metaphor. It is a direct physical consequence of supernova shockwaves compressing surrounding material into densities where gravitational collapse becomes possible. The second structure that defines our immediate neighborhood is one that was not clearly identified until 2020. When a team of astronomers using Gaia data published a result that genuinely surprised much of the field. They found that many of the most prominent star-forming regions in our part of the galaxy, clouds and clusters that had been studied individually for decades, were not randomly positioned. They were arranged in a coherent, wave-like structure, rising above and dipping below the average plane of the galactic disk in a regular oscillating pattern. The structure extended for roughly 9,000 light-years through the local galaxy. Its amplitude, the height of its peaks and depth of its troughs above and below the galactic plane, reached several hundred light-years, and it passed through or near an impressive list of familiar objects. The molecular clouds associated with Orion, the Perseus molecular cloud, the Taurus star-forming region, several other well-known concentrations of gas and young stars in our immediate galactic neighborhood. This structure was named the Radcliffe Wave, after the institute where the Discovery team was based. Before Gaia, it was invisible, not because it was not there, but because the three-dimensional precision needed to reveal the arrangement of those star-forming regions in space simply did not exist. Individual clouds had been studied in detail for decades. Their distances had been estimated, but the estimates were not precise enough, and the sample of objects with reliable distances was not large enough to reveal the coherent wave-like pattern connecting them. Gaia's billion-star catalogue made the pattern visible for the first time. The local galaxy is not a flat map, it is a wave, and the solar system is not sitting still while the wave surrounds it. Moving along its orbit around the galactic centre, the Sun is actively travelling through the Radcliffe wave structure. Some estimates suggest the solar system may currently be near a node of the wave, a point where the structure crosses the average galactic plane. Over millions of years, the Sun's position relative to the wave shifts, bringing it closer to or farther from the denser concentrations of molecular gas and star-forming activity that mark the wave's peaks. The neighbourhood changes as the solar system moves through it. Home is not a stable environment on these timescales. Now look up from the abstract structures and find the specific lights. On a clear winter night in North America, below the 3 stars of Orion's belt, there is a faint smudge barely visible to the naked eye. That smudge is the Orion Nebula. It sits roughly 1,300 light-years from Earth, well within the Orion Arm, and it is a region of active star formation happening right now. Dense molecular gas is collapsing under gravity, producing new stars, some of them surrounded by disks of material that may be forming planets at this moment. The ionizing radiation from newly formed massive stars is causing the surrounding gas to glow, which is what makes the nebula visible from Earth across 1,300 light-years of space. The light you see when you look at the Orion Nebula left it before the first cities appeared on Earth. Those stars forming inside it right now, the ones whose radiation is lighting up the surrounding gas. Some of them did not exist when Rome fell. The Orion Nebula is not a distant decoration. It is a window into the ongoing process of stellar birth happening inside the same arm of the galaxy the solar system lives in. Close enough that its light has been reaching human eyes for thousands of years without anyone fully understanding what they were looking at. Some of the most familiar lights in the winter sky are not decorative. They are nearby evidence of the structure we live inside. But knowing the neighbourhood is not the same as understanding its scale. There is a specific kind of frustration that comes from knowing a number without being able to feel it. You run into it constantly with cosmic distances. Someone tells you the Sun is 93 million miles from Earth. You understand the words. You can do arithmetic with that number if you need to. You can compare it to other numbers. But you cannot feel 93 million miles the way you can feel the distance across a room or the drive from one city to another. The number sits correctly labelled in your mind, available for recall and calculation, but emotionally inert. It does not connect to anything your nervous system has ever directly experienced. This is not a personal failure. It is a biological one, and being precise about why it happens matters before trying to do anything useful with it. Human beings evolved to navigate a world measured in feet and miles, in walking distances and hunting distances, and the time it takes to travel from one familiar place to another at the speed a human body moves. The neural machinery that makes distance feel real, that produces the gut-level sense of how far away something is, was calibrated by millions of years of experience operating in that range. It works with remarkable precision for the distances it was built for. It breaks down completely at cosmic scales, not gradually, completely. A number like 1 light-year, which is roughly 5,890,000,000,000 miles, does not feel like any distance at all. It is just a large label attached to an incomprehensible quantity. The Orion Arm is measured in thousands of light-years, so when you try to grasp its scale, you are not working slightly above the range of normal human experience. You are working in a register where the equipment your brain uses to process spatial scale has simply stopped functioning as designed. The numbers are real. The arithmetic is correct. The felt sense of what those numbers mean is not available, and no amount of concentration will make it available in the way that physical distance is available to direct experience. What you can do instead is reason about the scale carefully enough to understand something specific and important, why the map is so hard to build. why the debate about the arm's character has taken as long as it has, and why settling it requires instruments that operate at the absolute limits of human technological capability. Start with the nearest star. Proxima Centauri, the closest star to the Sun, is roughly 4.2 light-years away. The New Horizons spacecraft, launched in 2006 and now the fastest human-made object that has travelled beyond the planets, moves at roughly 36,000 miles per hour. At that speed, reaching Proxima Centauri would take approximately 78,000 years, a journey that would outlast all of recorded human civilization by a factor of roughly 8. Using the fastest vehicle we have ever built, covers a distance of 4.2 light-years. That is the gap to the nearest star. Now consider that the Orion Arm, depending on the model used and the direction measured, is estimated to span somewhere between a few thousand and possibly more than 20,000 light-years in length. Some analyses using recent Gaia data have traced coherent features in the local arm extending to distances of 10,000 light-years or more from the Sun in certain directions. A working estimate for the arm's width in the region near the solar system places it at several thousand light-years across. If you use 10,000 light-years as a conservative estimate for the arm's length, that distance is roughly 2,300 times the distance to Proxima Centauri. The journey to the nearest star, already 78,000 years at our fastest speed, multiplied by 2,300, gives you a crossing time for the arm of roughly 180 million years. At the speed of New Horizons, 180 million years ago, the Jurassic period was just beginning. The first true mammals had recently appeared. Dinosaurs were diversifying into the forms that would dominate terrestrial vertebrate life for the next 115 million years. The Atlantic Ocean was a narrow seaway barely opening between what would become North America and Africa. No grass existed, no flowering plants, nothing recognizable as the world you inhabit. That is the crossing time for one estimate of the Orion Arm's length. Using our fastest spacecraft, at the speed of light, the crossing takes 10,000 years. In 10,000 years, human civilization went from the first cities in Mesopotamia to the present day. Every empire that has ever risen and fallen, every language that has ever been spoken, every discovery in all of recorded science, every building ever raised, and every one that has crumbled back to Earth, all of it fits inside the time light needs to travel the estimated length of the structure we live inside. Now hold that scale and think about what it means for the project of mapping this structure from a single point inside it. The Gaia satellite measures stellar parallax, the tiny apparent shift in a star's position caused by Earth's annual orbit around the Sun, with extraordinary precision for stars within a few thousand light-years. These measurements are extraordinarily accurate, but parallax shifts become smaller as distance increases, and measuring smaller shifts requires higher precision for stars at distances of 5,000, 10,000, or 15,000 light-years. The parallax shifts are so tiny that even Gaia's instruments begin to accumulate meaningful uncertainty. The far reaches of the Orion Arm, the regions where the most important structural questions live, the questions about how long the feature extends and where it ends, sit at or beyond the distance range where Gaia's parallax technique delivers its highest confidence. This means the tools that have most dramatically improved our understanding of the local arm in recent years begin to lose their sharpest precision precisely at the distances where the hardest questions are located, tracing the arm's full extent, determining where it ends and where the interarm gap begins, measuring its pitch angle and curvature across its entire length, requires combining Gaia's precise nearby measurements with other techniques that reach farther but carry larger uncertainties. Radio surveys of molecular gas, infrared photometry of massive young stars, maser parallax measurements at selected star-forming regions. Each technique has its own range, its own systematic uncertainties, its own modelling assumptions that must be justified and tested. Combining results from multiple methods into a coherent picture requires careful analysis of where the datasets agree and where they diverge. And why? The fact that different research groups using different data combinations have reached somewhat different conclusions about the arm's extent and character is not a sign that something is wrong with the science. It is a sign that the problem is genuinely hard, that the measurements are operating near their limits in the most critical regions, and that the answer is not yet determined with the precision needed to end the argument. There is one more dimension to the scale problem that tends to get overlooked. The Orion Arm is not a static structure being measured from a stationary platform. It is a feature in a rotating galaxy, and the solar system is orbiting the galactic center at roughly 515,000 miles per hour. Over timescales of millions of years, the solar system's position within the arm changes, even over the timescales of a human scientific program. Spanning decades, the sun moves through space by an amount that is small relative to the arm's total dimensions, but not entirely irrelevant for the highest precision measurements. The thing being mapped is moving. The mapper is moving. The galaxy in which both are embedded is itself continuously evolving. There is no still frame. There is no moment when everything holds position long enough to be measured without the measurement itself becoming outdated. The map is always a snapshot of a moving system, taken by an instrument in motion, trying to describe something that will not hold still. If light needs thousands of years to cross the structure we call home, then no human lifetime can ever experience it as a place. It can only be inferred, measured, and drawn, and a structure dismissed as a spur can look very different once you begin to understand how far it actually reaches. Here is something almost never said clearly in popular descriptions of the solar system's position in the galaxy, even though it is completely true and changes nearly everything about how you should think about where we live. The solar system is not parked. When people talk about where the sun is in the Milky Way, the language defaults to the static. We are located in the Orion Arm. The solar system sits in this region. Our position in the galaxy is here. The vocabulary of location and address implies stability, a fixed relationship between an occupant and a place. Your house is at a specific spot on a specific street. It was there yesterday and it will be there tomorrow. The concept of address carries an assumption of permanence. A galactic address is not a pin on a map. It is a moving relationship. The Sun has been orbiting the center of the Milky Way since it formed roughly 4.5 billion years ago. Its orbital speed is approximately 515,000 miles per hour. That number sits outside ordinary experience the same way cosmic distances do. So try to connect it to something tangible. In the time it takes you to read a single sentence out loud, the entire solar system, every planet, every moon, every asteroid, every comet, every spacecraft humanity has ever launched, has moved roughly 150 miles along its orbital path around the galactic center, not relative to nearby stars, which are also moving, 150 miles through the galaxy itself. One full orbit of the Milky Way takes the solar system approximately 230 million years. Astronomers call this a galactic year, or a cosmic year. It is the fundamental unit of time for the solar system's relationship to the galaxy, the way a day is the fundamental unit of Earth's relationship to the Sun. In the 4.5 billion year history of the solar system, it has completed roughly 20 of these orbits. But the orbital motion is only the first layer of movement in this picture, and in some ways the least surprising one. The more consequential point for understanding the Orion Arm is what happens when you think carefully about what kind of structure the arm actually is and how a solar system relates to it over time. Most people, when they think about the solar system living inside the Orion Arm, carry a mental image, something like a train on a fixed track. The solar system is the train. The arm is the track. The train moves along the track, staying inside the arm because the arm is a solid structure with defined walls and the train follows along within it. That image is wrong in an important way. Spiral arms are not solid structures. They are not walls or corridors or fixed tracks. They are regions of enhanced density, places where gas and stars are more tightly concentrated than in the spaces between arms, driven by gravitational dynamics that create compression waves rotating through the galactic disk. The material inside a spiral arm at any given moment is not the same material that was inside it millions of years ago. Stars and gas clouds orbit the galactic center on their own trajectories, and those trajectories carry them into regions of higher density and then out again, on timescales determined by their individual orbits. The best comparison available in ordinary human experience is a traffic jam on a freeway. Imagine a stretch of highway where traffic slows for some reason. A curve, a change in the speed limit, an obstacle. Cars approaching from behind slow down as they reach the congested section, bunch up, travel through the jam at reduced speed, and then accelerate away on the other side. The jam as a feature of the road persists, even as the individual cars constituting it are constantly changing. A car that was in the jam 10 minutes ago is now a mile down the road. A car that was not in the jam 10 minutes ago has since entered and passed through it. The jam is real. It has a location. But it is not made of specific cars. It is a pattern sustained by the dynamics of the road. Spiral arms may work by an analogous mechanism. Gas clouds moving along their orbits encounter regions of enhanced gravitational compression, slow down and pile up, reach densities high enough to trigger star formation, and eventually move through and out the other side. The arm as a visible feature persists because the compression pattern persists, driven by the underlying gravitational dynamics of the rotating disk, not because the same material is permanently contained within it. In many models, the solar system's relationship to the local arm is better understood as passage through a moving pattern than as permanent residency inside a fixed structure. This matters for understanding the history of Earth's galactic environment. There have been periods in the geological past when the solar system was more deeply embedded in regions of the arm, with higher densities of molecular gas and more active nearby star formation. There have been periods when it occupied quieter regions. The galactic environment Earth has experienced over 4.5 billion years is not uniform. It reflects the solar system's journey through varying parts of the galactic landscape, moving through different sections of the arm's density distribution as the Sun follows its long orbital path. Now take this understanding of motion and apply it to the most familiar feature of the winter sky, Orion, the constellation that dominates winter evenings across the northern hemisphere. The 3 stars of the belt, the red of Betelgeuse at the upper left, the blue-white of Rigel at the lower right, the faint smudge of the Orion Nebula below the belt. This pattern has been recognized and named by human cultures across thousands of years. Ancient Egyptians knew it. The Babylonians charted it. Indigenous peoples across North America, Australia, and Africa incorporated it into their understanding of the sky. Orion feels permanent, written into the sky rather than dependent on where you happen to be standing. But Betelgeuse is roughly 700 light-years from Earth. Rigel is roughly 860 light-years away. In a somewhat different direction, the 3 belt stars range from about 800 to over 1,000 light-years in distance, each at a slightly different position in 3-dimensional space. They appear to form a coherent pattern only because of the specific angle from which we are currently viewing them. From this particular point in the solar system's long orbital arc, at this particular moment in galactic time, move the solar system a few tens of millions of years along its path, and the geometry of those stellar positions changes relative to our new vantage point. The belt loses its neat alignment. The shoulder and knee stars shift. The pattern that has felt eternal to every human who ever lived is a perspective effect of our current location and our current moment in galactic history. As temporary as the view from a moving car window, the night sky we have always known is a temporary arrangement. Every constellation is this, every pattern drawn on the sky, every story told using the stars as reference points, reflects the contingency of where the solar system happens to be right now in its orbit. And when it happens to be there in the galactic timeline, in 100 million years the night sky from Earth will be unrecognizable. The familiar patterns will be gone. New ones will have taken their place. And this applies to the Orion Arm in a way that deepens the question of what kind of place it is. If the arm is a density wave pattern rather than a fixed container, and if the solar system is passing through it rather than permanently residing inside it, then what we are trying to map is not a stable object in the way a mountain range is stable. It is a pattern sustained by dynamics that are themselves changing over time. The arm existed before the solar system entered its current region. It will persist in some form after the solar system moves through, but the specific configuration of gas and stars and structure that surrounds us right now is a snapshot of a pattern in motion, not a permanent address in a permanent place. Orion, the constellation, is a picture we drew on the sky from where we happen to be standing. Orion, the arm, is the place we live, and it is only beginning to be understood. But if our address is moving, what exactly are we moving through? The Orion Arm is not empty space with stars scattered through it. That picture, the one where you imagine dark emptiness punctuated by distant points of light, is one of the most persistent and misleading mental models in popular astronomy. The space between stars is not empty. It is filled with material in various states, various temperatures, various densities, at various stages of transformation. That material has a name, the interstellar medium, and the interstellar medium of the Orion Arm is not a passive backdrop. It is an active, continuously cycling environment that has been producing stars, losing stars, and rebuilding itself from the remains of stars for billions of years. Understanding what the arm actually is, as a physical place rather than a label on a map, requires following that cycle, because the cycle is not just background context for the story. It is the process that produced the solar system, that produced Earth, and that produced, in the most literal and material sense possible, you. The cycle begins in cold and dark. In certain regions of the Orion Arm, interstellar gas and dust accumulate over millions of years into structures called molecular clouds. These are not thin wisps of gas. The densest of them contain hundreds of thousands or even millions of times the mass of the Sun, compressed into regions spanning tens to hundreds of light years across. Inside a molecular cloud, the temperature drops to within a few tens of degrees of absolute zero. The density is high enough that the cloud's own material shields its interior from the ultraviolet radiation that would otherwise break apart the complex molecules forming there. In that cold, dark, shielded interior, chemistry happens on a scale and with a complexity that would be impossible in more exposed regions of space. Hydrogen bonds with hydrogen to form molecular hydrogen, the most abundant molecule in the universe. Carbon and oxygen combine to form carbon monoxide, one of the key tracers radio astronomers use to map the locations of molecular clouds across the galaxy. More complex molecules assemble, some of them organic in structure, chains and rings of carbon and hydrogen and nitrogen and oxygen that represent chemistry as sophisticated as anything in a laboratory. Molecular clouds are cold and quiet, but they are among the most chemically active environments in the galaxy. And when a region inside a molecular cloud becomes dense enough, when the local gravitational force pulling inward finally exceeds the thermal pressure pushing outward, something irreversible begins. The cloud collapses. The collapse does not happen uniformly. It fragments as it proceeds, with different regions falling inward at different rates, forming dozens or hundreds of individual collapsing cores simultaneously. Each core heats as it contracts, converting gravitational energy into thermal energy with increasing efficiency as density rises. The temperature at the center climbs from a few degrees above absolute zero to thousands of degrees, then tens of thousands, then millions. At roughly 10 million degrees, hydrogen nuclei begin fusing into helium, and the energy released by that fusion halts the collapse. A star ignites. This is happening right now, inside the Orion Arm, at distances close enough that the light from newly forming stars is reaching Earth. The Orion Molecular Cloud Complex, the enormous region of gas and dust associated with the constellation Orion, sits roughly 1,300 light-years from the solar system. Within it, the Orion Nebula represents a region where newly formed massive stars are so hot and luminous that their ultraviolet radiation is ionizing the surrounding gas, causing it to glow in the distinctive pinks and reds of energized hydrogen. The bright stars visible in the core of the nebula, a compact grouping called the trapezium cluster, are among the youngest massive stars visible from Earth. Some are less than 1 million years old. There are stars forming inside the Orion Arm right now. There are stars within 1,000 light-years of the solar system that did not exist when the Roman Empire fell. Their light is arriving at Earth now for the first time, carrying information about the process of stellar birth that the arm has been sustaining without interruption for billions of years. That is one end of the cycle. The other end is not quiet. Massive stars burn through their nuclear fuel with an extravagance that makes the Sun look patient. Where the Sun will spend roughly 10 billion years fusing hydrogen in its core. A star 10 times more massive exhausts its fuel in tens of millions of years. A star 20 times more massive does it in a few million. The more massive the star, the shorter the life and the more violent the death. When a massive star exhausts its core hydrogen, the events that follow happen fast. The core collapses in less than a second. The outer layers of the star, which may contain several times the mass of the Sun, fall inward toward the collapsing core and then rebound outward in an explosion of staggering energy. A supernova. At peak brightness, a single supernova can outshine an entire galaxy. The energy released in those few seconds equals what the Sun will radiate over its entire 10- billion year lifetime. But the light is not the most consequential part of a supernova for the surrounding environment. The shockwave is, as the explosion expands outward from the dying star, it sweeps up the surrounding interstellar medium, compressing it, heating it, and seeding it with the elements forged in the star's core during its lifetime. Carbon, oxygen, neon, silicon, iron. The heavy elements that make up rocky planets and the chemistry of biology are not present in the universe by default. They are manufactured by nuclear fusion in stellar interiors and returned to the interstellar medium by stellar winds and supernova explosions. Every atom, heavier than helium in the observable universe, was made inside a star. The supernova is the mechanism by which those atoms rejoin the interstellar medium, where they become available for incorporation into the next generation of stars and planetary systems. The local bubble, the cavity the solar system currently inhabits, was carved by a sequence of supernovae in this region of the Orion Arm over the last several tens of millions of years. The shockwaves from those explosions swept surrounding gas outward, heated it to millions of degrees, and left behind the hot, thin interior that the solar system drifted into a few million years ago. At the boundary of the bubble, where ancient shockwaves compressed the surrounding medium before losing their energy, new molecular clouds formed in the compressed material. Star formation began in those clouds. Some of the star-forming regions we can observe today near the bubble's boundary may owe their existence, at least in part, to the compression triggered by explosions that happened millions of years before they ignited. The stars that died to carve our neighborhood may have triggered the birth of the star-forming regions we observe today. This is the cycle in its full form. Molecular cloud collapses into a cluster of new stars. The most massive of those stars burn fast and die violently. Their deaths enrich the surrounding gas with heavy elements and compress it into new configurations. New clouds form in the compressed material. New stars ignite. The cycle runs continuously on timescales of tens of millions of years per iteration, driven by the same gravitational and thermodynamic processes that have been operating since the first stars formed in the early universe. Now comes the piece that connects everything to what we actually are. Whether or not the Sun was born in the exact region we now call the Orion Arm, it formed from the same galactic cycle of cloud collapse, stellar birth, stellar death, and chemical enrichment that the arm still displays today. The gas that collapsed to form the solar system was not made of pristine hydrogen and helium. It was enriched by generations of stars that had already run the full cycle, forging heavy elements in their interiors and scattering them into the interstellar medium when they died. The rocky inner planets of the solar system, including Earth, formed from solid materials in that enriched cloud. The oceans formed from water whose hydrogen was primordial but whose oxygen came from stellar nucleosynthesis billions of years in the past. The organic chemistry that eventually gave rise to life depended on carbon and nitrogen and phosphorus that were all produced inside stars that no longer exist. We are not simply living among the remains of stars. We are one of the things those remains became. The carbon in your body was forged in the core of a star that died before the solar system existed. The oxygen in your lungs was synthesized in stellar interiors and distributed by stellar winds and supernova explosions across billions of years. The iron in your blood traces back to the violent death of a massive star, somewhere in the history of the galaxy, long before the sun ignited. You are not separate from the cycling process of the Orion Arm. You are a local, temporary product of it, a specific arrangement of stellar material that has passed through nuclear fires, through shock waves, through cold molecular clouds, through the collapse of a protostellar nebula, before ending up organized into the form that is reading these words. The dust that hides the Orion Arm from our telescopes is made of the same material that built the world you live on. Stay with that for a moment before moving on, because the arm that is so large it defeats our instruments, so complex it resists our best maps, so uncertain in its own classification that researchers still argue about its name, is also the environment whose multi-billion-year history of creation and destruction produced the specific chemistry that allowed something like you to exist inside it. And inside this nursery and graveyard, we occupy a stranger position than most maps suggest. If you ask most people where inside the Orion Arm the solar system is located, the answers fall into a few predictable categories. Some say they have no idea, which is honest. Some say somewhere in the middle, which feels reasonable. A few who have read something about galactic astronomy say near the inner edge, which is closer to the current picture but needs unpacking. Almost nobody, regardless of background, has a working intuitive sense of what it means to be at a specific position inside a spiral arm. Because the concept of position inside a spiral arm is not like the concept of position inside any structure that ordinary human experience has prepared us to reason about. The current picture, drawn from the best available measurements, suggests the solar system does not sit at the geometric center of the Orion Arm in cross-section. It appears to be offset toward one side, specifically toward what some researchers describe as the inner boundary of the structure, the side facing the galactic center rather than facing away from it. Several analyses of maser astrometry data, the precise radio distance measurements to star-forming regions discussed in earlier chapters, place the Sun in a position where the denser concentrations of young stars and molecular gas characteristic of the arm's interior are distributed more prominently in certain directions than others. The side toward the Sagittarius Arm, which runs between us and the galactic center, shows fewer nearby concentrations of the material that defines the arm's core. The side toward the outer galaxy shows more. In some models, the solar system appears closer to the inner boundary of the local arm than to its outer boundary. But before that can mean anything useful, the concept of boundary needs to be looked at carefully. A spiral arm's boundary is not like any boundary that ordinary language is built to describe. The edge of a country is a line on a map, backed by legal agreement and enforced at specific points. You cross it and you are in a different jurisdiction. The edge of a city is less precise but still recognizable as a transition. Drive away from any major American city in any direction, and at some point the density drops. The buildings give way to suburbs. The suburbs give way to roads running through open land. And you know you have left, even if you cannot identify the exact moment of departure. These transitions are real and locatable in a practical sense. The boundary of a spiral arm is neither of these things. A spiral arm is defined by a region where the density of certain traces is higher relative to the surrounding interstellar medium. Young, massive stars that live only a few million years before exhausting their fuel. Star-forming regions where molecular gas is actively collapsing into new stellar systems. Dense molecular clouds. Ionized gas regions where young stars are heating surrounding material and causing it to glow. These are what astronomers use to identify spiral arms, because these features concentrate preferentially in the regions of higher density that define the arms. But these features do not end at a sharp boundary. The concentration of arm tracing material increases as you move into an arm and decreases as you move out. But the change is gradual. It happens over hundreds of light years. not over a line you can point to. There is no moment when you cross from outside the arm to inside it. There is only a progressive change in the density of the material around you, and the picture changes depending on which tracer you use. If you define the arm by the distribution of the youngest massive stars, you get one picture of where it is and how wide it is. If you use molecular gas as the tracer, you get a somewhat different picture. Warm dust emission gives another. Different tracers probe different aspects of the arm's physical character, and those aspects do not all have exactly the same spatial distribution. The arm is not a single object with a single boundary. It is a collection of overlapping distributions of different types of material, each with its own spatial extent and its own gradient from the arm's interior toward the surrounding medium. When researchers say the solar system may be near the inner edge of the local arm, they mean something like this. In several analyses, using several different tracers, the Sun appears to be in a position where the concentration of arm characteristic material is higher on one side, toward the outer galaxy, and lower on the other side, toward the galactic center. The inner side shows fewer nearby concentrations of dense molecular gas, fewer nearby active star-forming regions, fewer nearby young stellar populations. The outer side shows more. The solar system is not at the geometric center of the distribution of arm material. It is offset. The edge itself is not a line. It is a question. This positional ambiguity has a physical reality behind it that goes beyond the limitations of our measurements. The local bubble that the solar system sits inside is, by definition, a region of lower density than the arm's main body, because the supernovae that created it evacuated material from the immediate neighborhood. The solar system is inside the arm, in the sense that the arm's structure extends in multiple directions around it. It is near a boundary in the sense that the arm's characteristic material is not uniformly distributed in all directions from its current position. There is something worth sitting with in the geometry this creates. The solar system is not at the heart of the arm, not in the densest region, not near the most active star-forming complexes, not in the most unambiguously interior part of the structure. It is not outside the arm in any definitive sense either. It sits in a specific, historically contingent, offset position inside a structure whose boundaries are gradients, whose full extent is actively debated, and whose character the field is still working to determine. We are close enough to the arm to be part of it, shaped by its history and built from its material. We are offset enough from its densest regions that the most active parts of the structure, the richest star-forming complexes, the greatest concentrations of young stars, are concentrated in specific directions rather than surrounding us evenly. We live near a gradient rather than at a center. We inhabit a transitional position rather than a representative one. The solar system is not in the center of the arm. It is not outside it. It seems to live near one of its uncertain edges, close enough to belong, far enough to feel displaced. And that edge is not a line. If the edge is uncertain, then the arm itself may not be what we thought. In December of 2013, a rocket carrying a satellite roughly the size of a small car lifted off from the Gaia Space Center on the northeastern coast of South America and headed for a gravitationally stable point in space called Lutu, about 1 million miles from Earth in the direction away from the Sun. The satellite was Gaia. Its mission, reduced to its simplest possible statement, was to measure where stars are. Not a few stars, not a few thousand, more than 1 billion stars, with a precision that had never been approached before in the history of astronomy. The number sounds straightforward. The engineering required to achieve it was anything but. To understand what Gaia's precision actually means at a physical level, consider the following. The satellite was designed to measure the angular positions of stars with an accuracy of a few microarcseconds for its brightest targets. 1 microarcsecond is 1/millionth of 1 arcsecond. 1 arcsecond is 1/3600th of a degree. At that level of angular precision, Gaia could in principle detect the apparent shift in a star's position caused by an object the size of a human fingernail held at the distance of the moon. That is not a poetic exaggeration. It is a rough physical translation of the angular scale the mission was operating at. The technique Gaia used to convert those angular measurements into distances is called parallax. As Earth moves around the Sun over the course of a year, nearby stars appear to shift slightly in position against the background of more distant stars. The size of that shift depends inversely on the star's distance. A star twice as far away shows half the parallax shift. Measure the shift precisely enough and you have the distance through pure geometry, without any assumptions about what kind of star you are looking at. Before Gaia, precise parallax distances had been measured for a few 100,000 stars, mostly within a few thousand light years. Gaia extended that reach to more than 1 billion. The first major data release came in 2016 and provided positions for more than 1 billion sources. The second release, in 2018, added full parallaxes and proper motions for more than 1,300,000,000 stars. The third release, in 2022, refined those measurements further and added new data on stellar chemistry, binary systems, and variable stars. Astronomers who had spent entire careers working with catalogues of thousands of precisely measured stars found themselves suddenly holding catalogues of more than 1 billion. The effect on the picture of the local galaxy was immediate and ongoing. The most reliable traces of spiral structure are open clusters, groups of young stars that form together from the same molecular cloud within the last few 100 million years, and that reliably mark the locations where star formation has recently been active. Before Gaia, the distances to most open clusters were estimated from photometry, comparing how bright the stars appeared to how bright similar stars were known to be and working backward to a distance. These photometric estimates carried uncertainties large enough to blur the three-dimensional arrangement of clusters into ambiguity. Gaia replaced those estimated distances with geometric measurements for thousands of clusters simultaneously, and the three-dimensional picture of the local spiral structure came into a new kind of focus. What that focus revealed about the Orion Arm was not what the Spur model had predicted. Several research groups, working independently and publishing results in the years following Gaia's second and third data releases, found a local arm that was longer, more coherent, and more structurally organized than classic maps showed. A 2019 study using Gaia data combined with catalogues of young massive stars traced a feature in the local arm, extending to distances that sit uncomfortably with casual use of the word spur. A 2021 analysis using open clusters found a coherent spiral feature in the local arm region with a pitch angle of roughly 11 degrees, falling within the range of pitch angles measured for the major arms of other well-studied spiral galaxies. The language in these papers shifted noticeably. Researchers who had routinely written Orion Spur in earlier work began writing Orion Arm or local arm instead, not as a stylistic choice, but as a considered reflection of what the improving data supported. But here is where the story demands precision rather than forward momentum. The Gaia data did not settle the debate. It sharpened it. The same data releases that revealed the local arm to be longer and more organized than older maps suggested also revealed the Milky Way itself to be more complicated, more asymmetric, and less cleanly structured than any simple model had predicted. The galactic disk is warped. It does not lie flat. It curves upward on one side of the galaxy and downward on the other in a way that increases with distance from the center and that varies with direction. The spiral pattern, viewed through Gaia's precise three-dimensional measurements, shows irregularities in substructures and asymmetries that are not present in idealized density wave models. There are stellar streams, coherent groups of stars moving together through the disk that represent the disrupted remnants of smaller systems accreted over billions of years, threading through the local galaxy in ways that complicate the identification of clean spiral features. In this more complex picture, the question of what constitutes a genuine major spiral arm becomes harder to answer, not easier. A true major arm in the dynamical sense involves not just a concentration of young stars and gas, but a self-sustaining density wave pattern, a gravitational compression feature that propagates through the disk and persists over many galactic rotations. Demonstrating that the Orion Arm meets that criterion requires more than showing it is long. It requires showing that its velocity field carries the signature of density wave dynamics, that the motions of gas and stars within it reflect the expected patterns of material flowing into and through a compression feature. Some analyses of Gaia velocity data have found signatures in the local arm region consistent with density wave structure. Others have found the picture more ambiguous. The field has not reached consensus, and the measurements needed to resolve the question definitively sit at the edge of what current data can support. The Radcliffe wave, discovered in Gaia data and published in 2020, illustrated both the power and the complexity of what the mission revealed. The 9,000 light-year undulating structure of gas and star-forming regions had been invisible to every previous survey. It became apparent only when precise three-dimensional positions were available for enough objects to reveal the pattern connecting them. Its existence demonstrated that the local galaxy contained large-scale structures that nobody had predicted or suspected, waiting to be discovered once the measurement precision reached the level needed to see them. That discovery is a reminder that the map will keep changing, not because researchers have been careless or wrong in their previous work, because each improvement in measurement precision reveals structure that the previous level of precision could not see. The galaxy that Gaia has shown us is richer and more complex than the galaxy visible to previous instruments. The galaxy that future instruments reveal will be richer and more complex still. The answer is not that the old maps were wrong. The answer is that the old maps were simpler than the galaxy. Gaia's accumulated data continues to be processed and reanalyzed. The mission's fourth major data release will provide refined astrometry for an even larger sample of stars, with improved precision in the proper motion measurements that allow researchers to trace the dynamical history of stellar populations in the galactic disk, the specific questions that current data leaves unresolved about the Orion Arm, the arm's dynamical signature, its full coherence at distances beyond a few thousand light-years, the relationship between its structure and the galaxy's large-scale density wave pattern, will be addressable with greater precision when that data becomes available. The map of our galactic neighborhood will be redrawn again. Some current uncertainties will narrow. New ones will open up as the improving measurements reveal details that the current data cannot resolve. This is not a sign that the project is failing. It is the expected result of applying honest measurement to a genuinely complex system. The map was changing, but it was also moving through time. Chapter 7 changed the map from still to moving. This chapter changes the moving map into time. The solar system orbits the center of the Milky Way at roughly 515,000 miles per hour. One complete orbit takes approximately 230 million years. Astronomers call this a galactic year. It is the fundamental unit of time for the solar system's relationship to the galaxy, the way an Earth year is the fundamental unit of Earth's relationship to the seasons. The solar system has completed roughly 20 of these orbits since it formed. Hold that number and think about what 20 galactic years actually means in terms of the history of life on this planet. 1 galactic year ago, the solar system was completing a different arc through the galaxy's structure. On Earth at that time, the most catastrophic extinction event in the planet's history had just occurred. The end Permian extinction had wiped out more than 90% of all marine species and roughly 70% of terrestrial vertebrate species. The cause is still debated by researchers, but the scale of the destruction is not. More than 9 out of 10 species in the ocean were gone. The continents were still assembled into the supercontinent Pangaea, just beginning the slow fracturing process that would eventually produce the geography we recognize today. The earliest dinosaurs were just beginning to appear in the fossil record. No mammal recognizable as a mammal existed anywhere on Earth. That is where this planet was 1 galactic year ago. 2 galactic years ago takes us to the Carboniferous period. Vast tropical forests covered much of the land surface, and the organisms capable of efficiently decomposing woody material had not yet evolved, which meant dead trees accumulated on a scale that produced the coal seams the Industrial Revolution would later mine. Oxygen levels in the atmosphere were significantly higher than today, high enough that insects, which breathe through passive diffusion rather than active pumping, could reach sizes impossible in the modern atmosphere. Dragonflies with wingspans approaching 2.5 feet patrolled the air. Giant millipedes several feet long moved through the undergrowth. No reptiles. No mammals. No birds. Nothing that any human being would recognize as a relative. 3 galactic years back reaches the Devonian, the age when the first vertebrates were making tentative excursions onto land from the ocean. 4 galactic years reaches the Silurian. 5 reaches the Ordovician. 6 reaches the boundary of the Cambrian. When most major animal body plans appeared in the fossil record for the first time, the moment when complex multicellular life suddenly became visible, the entire history of complex animal life on Earth, from the Cambrian explosion to the present day, spans roughly 600 million years, roughly 2.5 galactic years. The entire span of anatomically modern humans on Earth, roughly 300,000 years, is approximately 1/800th of a single galactic year. The entirety of recorded human history, from the first cities to the present day, is roughly 10,000 years. If a galactic year were represented as a single Earth calendar year, all of recorded human history would occupy approximately 10 minutes of that year, clustered in the last seconds of the last day. These comparisons are not included here to produce the familiar sensation of human insignificance in the face of cosmic time. That sensation is easy to produce and is not the point. The point is something more specific and more consequential for understanding what kind of place the Orion Arm is. Home is not only unfinished on a map, home is changing while we try to map it. The solar system has not always been in the same relationship to the Orion Arm's structure. Over the course of its 20 galactic orbits, the Sun has moved along its orbital path through regions of the arm with different densities of molecular gas, different rates of nearby star formation, different concentrations of young massive stars. The galactic environment that Earth has experienced over 4.5 billion years is not a uniform constant. It is a history of changing exposures to different aspects of the arm's activity as the solar system moves through varying regions of the galaxy's structure. Some researchers have explored whether those changing galactic environments left detectable traces in Earth's geological and biological record. The idea is not implausible. If the solar system passes through a region of the arm with significantly higher density of molecular gas, the increased density of the interstellar medium presses on the heliosphere, the bubble of solar wind that surrounds the solar system and partially shields it from interstellar radiation. A compressed heliosphere allows more cosmic rays to reach Earth. More cosmic rays interact with the upper atmosphere in ways that may affect cloud formation and, through that, climate on very long timescales. Some researchers have proposed correlations between the solar system's passage through denser galactic regions and periods of enhanced glaciation in the geological record. The evidence is suggestive but not yet definitive. The causal chains are long and the uncertainties are substantial. But the orbital mechanics are not in doubt. The environment changes as the solar system moves. And there is a further dimension to this that takes the idea of a moving address and extends it into something genuinely disorienting. The Orion Arm itself is not permanent on galactic timescales. Spiral arms form, persist, and eventually dissolve or are disrupted by gravitational interactions. The specific configuration of arms in the Milky Way at this moment in its history is not guaranteed to be the same configuration a billion years from now. The galaxy has been interacting gravitationally with satellite galaxies throughout its history. The Sagittarius dwarf galaxy has been partially disrupted and absorbed over billions of years. The Large Magellanic Cloud is close enough to be gravitationally interacting with the Milky Way's disk right now, pulling on the disk's outer regions in ways that contribute to the warp that Gaia's measurements revealed. These interactions affect the spiral pattern over time. In roughly 4.5 billion years, the Milky Way will begin merging with the Andromeda Galaxy. That merger will unfold over billions of years, a gravitational interaction in which the two galaxies interpenetrate, swing past each other, and eventually settle into a merged system. The spiral arms of both galaxies will be disrupted in that process. The Orion Arm, whatever its final classification and however far it extends, will not survive the merger in recognizable form. This is not imminent. 4.5 billion years is longer than the current age of the Earth. But the impermanence is worth registering because it completes the picture of what kind of thing we live inside. The arm is not an eternal feature of the galaxy. It is a pattern sustained by the current dynamics of the disk, subject to gradual change from interactions already underway, and finite on timescales that are enormous but not infinite. We are not mapping a statue. We are mapping a river that is moving through a larger body of water, changing course as it goes, carrying material that has been cycling through it for billions of years, flowing toward a destination that neither the river nor anyone standing in it can see. The map we make today is accurate for today. The river will shift. The map will need to be redrawn, not because the map is wrong, but because the river does not hold still. And somewhere inside that moving, unfinished map, there is a loneliness that scale alone cannot explain. There is a specific kind of disorientation that does not come from being lost. Being lost has a shape to it. You know you are lost. You have a destination in mind, a direction you are trying to find. And the problem is that you cannot locate the path. That is uncomfortable, but it is a problem with edges. It implies a solution somewhere. The right road exists. You just have not found it yet. What the solar system's position in the Orion Arm produces is something different and harder to name. It is not the disorientation of being lost. It is the disorientation of standing inside something so vast that the concept of outside has no practical meaning for you. You are not lost. You know roughly where you are. You are in the Orion Arm, near its inner boundary, inside the local bubble, orbiting the galactic center at 515,000 miles per hour, 26,000 light-years from a supermassive black hole. That is a substantial amount of positional information, and it still does not give you the thing the human mind most wants when it tries to locate itself. A view from outside. There has never been one. There will not be one in any time frame that connects to human experience. We are inside the structure, and inside is the only perspective that has ever existed for us. We are not temporarily inside, waiting for technology to improve enough to step out and look back. The structure is too large. The distance is too vast. The physics too uncooperative. The outside view is not a future achievement. It is a permanent absence. Now consider the specific geometry of what that absence defines. The solar system is not at the center of the Milky Way. The galactic center, with its dense stellar populations and its supermassive black hole called Sagittarius A star, sits 26,000 light-years away. Life near the galactic center would be a radically different experience. The density of stars in those central regions is orders of magnitude higher than in the outer disk. The radiation environment is far more intense. The gravitational dynamics are dominated by the central mass in ways that the quiet outer disk never experiences. We are not there. We are in the relative calm of the outer disk, where stellar densities are lower and the gravitational dynamics are the slow, steady orbital motion of a disk galaxy's outer regions. But we are not at the edge of the Milky Way either. The galaxy's disk extends for tens of thousands of light-years beyond our position. Beyond the disk, the stellar halo stretches even farther, populated by old stars on elliptical orbits that carry them far above and below the plane. We are not at the frontier looking outward into intergalactic space. We are somewhere in the middle of the disk, distant from the turbulent center and distant from the quiet outskirts, in a region that is neither extreme in any direction. Within the Orion Arm specifically, we are not at the center of the structure. We are offset toward the inner boundary, the densest. Most active regions of the arm lie in certain directions rather than surrounding us uniformly. We are in a cavity carved by supernovae, rather than in a representative sample of the arm's typical conditions. We are near a boundary that is not aligned, inside a structure whose classification is actively debated, in a position that is real and specific, and yet stubbornly resistant to any description that makes it feel settled. There is a word for this kind of position, not a scientific word, a human one, in between. The solar system lives in between in nearly every sense that word can carry. between the galactic center and the galactic edge, between the major arms of Perseus and Sagittarius, between the dense core of the Orion Arm and its uncertain outer boundaries, between the position that would be dramatic and the position that would be completely quiet, in a region defined less by what it is than by what it sits between. Every framework for cosmic self-location that human beings have constructed has eventually had to absorb displacement. Ancient models placed Earth at the center of everything. When that was overturned, new pictures placed the Sun at the center of the solar system, then the solar system somewhere significant in the galaxy, then the galaxy in some meaningful position in the universe. Each displacement was absorbed over time, built into a new accommodation that found meaning in a less central position than the last one. The Orion Arm continues that displacement in a quieter way. We are not at the center of the galaxy. We are not at its edge. We are not in one of its primary arms. At least, not definitively. And possibly not at all, depending on how the current debate resolves. We are in a structure whose character is uncertain, whose extent is still being measured, and whose name is still an argument. Our cosmic address comes with an asterisk, and the asterisk points to a footnote that is still being written. The loneliness this produces is different from the loneliness of scale that most cosmic content invokes. The loneliness of scale is the loneliness of smallness, of being a tiny organism on a small planet orbiting an ordinary star in a vast and indifferent universe. That feeling has been written about and painted about and set to music for as long as human beings have been thinking clearly about the cosmos. It carries a kind of dark grandeur. It is a real and important response to a real feature of the situation. The loneliness of the middle place is quieter and harder to articulate. It is not the loneliness of being small. It is the loneliness of being in a position that does not resolve into any clean narrative. You are not at the dramatic center of things. You are not at the austere edge of things. You are not even in a clearly defined feature of things. You are at an in-between address in an in-between structure in the outer middle of a galaxy whose own full character your best instruments are still working to determine. That uncertainty is not a failure of science. It is an accurate representation of where understanding currently stands. The map is incomplete because the territory is genuinely hard to map from the inside. The name is contested because the evidence genuinely supports more than one interpretation. The position feels unresolvable because the structure that defines it does not have sharp edges that resolve neatly when measured from a single point buried within them. Living with that uncertainty is not the same as being lost. The uncertainty is not something that went wrong. It is the honest shape of what we actually know about where we actually are. But being impossible to place completely is not the same as being meaningless. Begin with a number that will not fit inside any human mind, no matter how carefully it is handled. The Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that range, the gap between the low estimate and the high estimate, is itself larger than the total stellar count of most smaller galaxies. It is a number that can be written down, used in equations, compared to other large numbers. It cannot be held in the imagination as a quantity with genuine weight. The way you can hold the number of people in a room, or the number of days until a date on a calendar. The Orion Arm contains some fraction of those stars, hundreds of millions at minimum, possibly more, arranged across a structure that, depending on the model and the measurement, may span many thousands of light years in length and several thousand in width, filled with gas and dust and molecular clouds and star-forming regions and the full cycling machinery of stellar birth and death described in earlier chapters. Those numbers are real. They describe actual objects, actual nuclear furnaces operating under the same physical laws that have governed the universe since its first fraction of a second. The Orion Arm is not a metaphor or a human construction imposed on neutral space. It is a place. Vaste, complexe, ancien, active place that existed before the solar system formed and will exist, in some evolved form, long after the sun exhausts its fuel. And inside all of that, there is one star that would not appear on any list of the most remarkable objects in the Milky Way. It is a G-type main sequence star, middle-aged, middle mass, middle luminosity. It sits near the inner boundary of the arm, inside a bubble of hot, thin gas carved by ancient supernovae. Moving along its orbit around the galactic center at a distance and a speed that place it firmly in the category of unremarkable, its chemical composition is representative of stars that formed from enriched interstellar gas in the outer disk. Its age is neither unusually young nor unusually old. It does not have an exotic companion, a peculiar spectrum, or a record-setting luminosity. In any catalogue organized by scientific interest, it would be a background object, noted but not featured. Around that star, at a distance of 93 million miles, there is a rocky planet 8,000 miles in diameter. On this planet, somewhere between 3.5 and 4 billion years ago, something happened that has not been confirmed to have happened anywhere else in the Orion Arm, in the Milky Way, or in the observable universe beyond it. As far as any measurement made from this planet has been able to determine, chemistry became biology. Molecules began copying themselves. The copying was imperfect, which meant variation. Variation meant some copies were more effective at copying than others. Differential effectiveness over enormous timescales meant the slow, undirected accumulation of complexity in the copying systems. Single cells, cells with nuclei, multicellular organisms, nervous systems capable of modelling the world well enough to navigate it, and eventually, through the same blind process that had been running for billions of years, brains capable of doing something that no physical process requires, and that the universe gives no indication of valuing asking questions about where they came from. As far as we have confirmed, this is the only place in the Orion Arm where that sequence of events has occurred. Let that land before moving on. Not every star in the arm, not every region, not even every solar system with a rocky planet in a habitable orbit. This one, this specific point near the inner boundary of a structure whose name is still an argument, inside a bubble carved by dead stars, orbiting an unremarkable G-type star in the outer disk of an average spiral galaxy. The arm does not know this. The arm is gas and gravity and radiation, and the cycling of matter through nuclear fires and cold clouds. It does not have awareness. It does not assign significance. The meaning is entirely on our side of the relationship. But consider what that means. The Orion Arm produced, in at least this one confirmed location, a world where stellar material organized itself over 4 billion years into a form capable of looking back at the arm and asking what it is. The material of the arm is doing its own astronomy. The same carbon that was forged in stellar interiors and scattered by supernova shockwaves and incorporated into molecular clouds and collapsed into a protostellar disk and assembled into a rocky planet and metabolized by single-celled organisms for billions of years is now, in this one confirmed arrangement, constructing instruments to measure the structure of the arm it came from. That is what the Orion Arm contains. It contains every ocean that has ever existed on Earth, from the first shallow seas of the Archean to the deep Pacific basins of today. Every species that has ever lived, from the earliest self-replicating molecules to the organisms alive right now, in every corner of the biosphere, every extinction, every recovery, every radiation of life into newly emptied ecological space, every tree that has ever grown, every reef that has ever assembled itself from the chemistry of a warm, shallow sea. It contains every human civilization that has ever existed and every one that has ever fallen, every language that has ever been spoken, including the languages that disappeared before anyone thought to write them down, every song ever composed, every proof ever constructed, every building ever raised, every question ever asked beneath the stars, including every question ever asked about the stars themselves, including every question this account has been working through. On the galactic map, the Orion Arm is one feature among many. To us, it is every feature there has ever been. Whether the arm has produced this kind of complexity anywhere else, whether there are other worlds in this structure where chemistry became biology, and biology became awareness, and awareness became the impulse to map the galaxy. We do not know. The silence of the sky on that question is one of the most consequential silences in science, and it has not yet been broken. But the question is being asked, from this specific location, near the inner boundary of a structure whose classification is still contested, by a species made from the same stellar material the arm has been cycling through nuclear fires and cold clouds for billions of years. The arm generated something that maps the arm, and that brings us back to the picture that did not exist. Come back to the image. The spiral galaxy with the golden bar at the center, the 4 sweeping arms curving outward through the dark, the little marker near one of the outer arms with the label that says "You are here," the image painted by Robert Hurt at Caltech, built from radio surveys and infrared data and decades of careful inference. The image that is a hypothesis made visible, the image that is not a photograph. That image exists because someone looked at the absence of an outside view and decided it was not a reason to stop. The measurements existed. Hydrogen surveys and infrared observations and parallax catalogues and stellar population studies, incomplete and contested and subject to revision, but real. And someone decided that an honest map built from imperfect data, clearly understood to be a reconstruction rather than a photograph, was more valuable than no map at all. That attempting to represent what was known served the project of understanding better than waiting for certainty that would never fully arrive. That decision was correct, and it is being made again, right now, by every researcher working on the structure of the Milky Way. The absence of a picture did not stop us from building a map. At this moment, Gaia's accumulated data continues to be processed and reanalyzed by research teams around the world. The mission's 4th major data release will provide refined astrometry for an even larger sample of stars, with improved precision in proper motion measurements that allow researchers to trace the dynamical history of stellar populations in the galactic disk. The specific questions that remain unresolved about the Orion Arm, its dynamical signature, its full coherence at distances beyond a few thousand light-years, its relationship to the galaxy's large-scale density wave structure, will be addressable with greater precision when that data becomes available. And beyond Gaia, the Square Kilometre Array, an international radio telescope project building facilities across 2 continents, will eventually map the distribution of neutral hydrogen in the Milky Way with sensitivity and resolution that makes previous radio surveys look like early sketches. The maser astrometry programs that have been delivering precise geometric distances to star-forming regions will continue adding new measurements, extending the network of precisely located anchor points for the arm's structure. Each of these efforts is ongoing. People are doing this work right now, processing data, testing models, writing papers, arguing at conferences about what the numbers mean. The map is being actively revised, not because previous researchers were careless, because the measurements are improving, and a more complex truth is becoming visible through the improving precision. The Milky Way is 12 billion years old. It has been interacting gravitationally with satellite galaxies, accreting material, evolving under the combined influence of dark matter and stellar feedback and density waves for longer than the Earth has existed. It is under no obligation to be simple. The complexity that Gaia has revealed in the local galaxy is the complexity of a real system with a real history, not a sign that something went wrong with the science. The old maps were not built from carelessness. They were built from limited evidence, and the evidence has since improved. Each revision is honest. Each one is incomplete. The incompleteness is a permanent feature of the situation, not a temporary gap that will eventually close into a finished picture. Here is what that means at the level of the situation we all actually occupy. We are not outside the Milky Way looking back at our home. We are inside it, blinded by its dust, carried by its rotation, surrounded on all sides by stars and gas and the ongoing machinery of stellar birth and death. We cannot step out to get a cleaner view. We cannot wait for a more complete map before we have to live inside the structure. We are here now, in this specific in-between place, with this specific partial knowledge, making the best picture we can from where we stand. Think about what that actually is. From one rocky planet, orbiting an unremarkable star, near the inner edge of an arm whose name is still an argument, inside a bubble carved by stars that died before our sun was born. A species made from recycled stellar material has looked outward into the structure surrounding it and begun to understand the shape of the place it came from. Not completely, not without error, not without ongoing disagreement about the details, but genuinely, with real instruments producing real measurements, and real people spending real careers on the problem because they think the answer matters. The project of understanding where we are is not a luxury or an abstraction. It is the most fundamental question a conscious species can ask. And the fact that the answer is hard, that the structure resists simple description, that the map keeps requiring revision as the measurements improve, does not diminish the project. It defines it. It makes the mapping into the specific kind of achievement that it is something accomplished not from a comfortable overview, but from genuine immersion, under real constraints, with full knowledge of the limitations involved. The Orion Arm produced, in this one confirmed place, something that builds instruments to study the arm, something that is genuinely motivated to understand the structure that made it, that spends resources and time and human careers on the problem of figuring out the shape of home. Whether the arm produced anything similar anywhere else remains the deepest open question in science. But the fact that it produced this here, once, is not nothing. Go back outside tonight if you can. Find a dark enough sky and look up at that pale river of light again. You are not looking at a picture. You are looking at the actual structure, from the inside, from your specific position near its uncertain inner edge. At this specific moment in the sun's long orbit, you are looking at home, the only way home can ever be seen from where you are standing. And somewhere, right now, a researcher is processing data from 1 billion stars, trying to determine more precisely what kind of place it is. The map is not finished. It never will be. But we are the ones drawing it.